And ladies and gents, welcome back to another lesson, Chapter 12, Lesson 3, Solving Two-Step Inequalities. Notice the key, two-step. That'll be kind of similar to what we've been doing. Go ahead and pause your video. Come on back when you are ready. I'll go ahead and scroll down now. And let us go. All right, ladies and gents, if this looks familiar, it's because it is. Take a look at problems we did like yesterday and look at problems we did like today. The only difference is an extra number, a coefficient with that x. Now, of course, we could take that and build that up into multi-step inequalities. Maybe they have inequalities on both sides of the inequality symbol. And we can work with inequalities with more than one variable. But for today, our goal is to solve a two-step inequality, describe and graph its solutions. Go ahead and pause your video. Come on back when you're ready. So here we go with page 339, 28 to 45. I have three examples to show you. We're going to start with an inequality. Negative 3x plus 2 is greater than or equal to 7. All right, so where are we heading with this? First thing, you got a picture. Just like we had before, our goal is to isolate the x, get it by itself. So the question is, which number should we get rid of first? We always try to take rid of the constant, take care of the constant term first. So let's get rid of a positive 2 with a negative 2. Positive 2 and negative 2 make 0, leaving us with negative 3x is greater than or equal to 5. Think about 7 going up and 2 going down. That's why we get to 5. Now let's go ahead and get rid of that negative 3, right? So how are we going to get rid of that negative 3? The inverse of multiplying is to divide by, as soon as you see that, divide by a negative. Changes that inequality sign. Anytime you multiply or divide by negatives, it reverses the inequality symbol. All right, in the meantime, 3/3 cancels out, the opposite of a negative cancels out. What does that leave us with? An x less than or equal to. And you may write negative 5/3, but I think it would be more appropriate to write that as a mixed number, where any number x works as long as that number is less than or equal to negative 1. So let me go ahead and write in a few numbers here. And I'm going to go ahead and identify where is negative 1 and 2/3. It'd be right about here. Should we leave it an open circle or a closed circle? Well, it can equal negative 1 and 2/3. And where would all the numbers be that are smaller than that? Well, that would include negative 2, negative 2.5, negative 2.9, negative 3, negative 3 trillion, and so on and so on. Now, if you don't believe it, you are always welcome to check. So let me write negative 3 times some number x plus 2 greater than or equal to 7. Negative 3 times some number x plus 2 greater than or equal to 7. And we're going to pick one number on each side of that dot, of that circle. And I got to tell you, I almost always start with 0, right? 0 just is one of the easiest numbers to compute. And then maybe on the other side, we can do negative 3, just for the heck of it. Now, negative 3 times 0 is 0. 0 plus 2 is 2. So we ask ourselves, true or false, 2 is greater than, well, 2 is not greater than 7. 2 is not equal to 7. So this is a false statement. Therefore, numbers like 0 you would not shade in. It's not a solution. Meanwhile, 3 sets of negative 3 would be negative. No, Mr. Cowan, the opposite of all those negatives would be positive 9. And 9 plus 2 is 11. So true or false? Well, that's a true statement. So you would color in negative 3, and of course you'd color in negative 2, and you'd color in negative 1.99, you'd color in negative 2 and 1/17, and so on. All these numbers would be solutions. And so instead of drawing trillions and trillions and trillions of dots, little points, we just connect them all, kind of blur them together. That, ladies and gents, is why we draw a ray. Let's do another example. Our goal is to isolate the x, get it by itself and alone, so we're going to get rid of the minus 5. First thing to do is get rid of a negative 5 with a positive 5. I don't know about you, but I like to change subtraction into adding the opposite. Now, that's just me. You don't have to. Subtract 5, add 5, make 0. And remember, anytime you add or subtract, that inequality sign does not flip around. We talked about that yesterday. So what does that leave us with? That leaves us with a third of an x is less than 3. Okay, but we don't want to know a third of an x is. So let's go ahead and multiply both sides by 3. I think I might have just accidentally erased my multiplication dot. 3/3 makes a single x. Notice multiplying by positive 3 does not flip the inequality sign around. And in this case, any number x works as long as that number is smaller than 9. Now, just for kicks, I might ask you to start doing this. Put 9 in the middle, put 2 numbers on each side. If you want to draw more, you may. Should we fill in the circle or leave it open? Well, it cannot. There's no or equal to sign. So leave that guy an empty circle. And where are all the numbers smaller than 9? Well, that would be this direction. Now make that ray thick and loud and proud. And again, if you don't believe me, you can always recopy that. And we're going to substitute in numbers. One number on each side. You know Mr. Callan, he says he's in love with 0. At least 0 makes it easy to compute, because 0 divided by anything is 0. 0 plus a -5 is a -5. True or false? Well, that appears to be a true statement. -5 is in fact shorter or smaller than -2. So that verifies so far that we should have shaded to the left. What about picking, how about 12? 12 will divide quite nicely here, won't it? So 12 divided by -3 is -4. -4 together with the -5 is a -9. All right, give me a second. What went wrong? Oh, Mr. Callan, that's not a negative symbol in the first place. Wake up. So my apologies. That said a +3. Now, the good news here is 0 divided by anything is still 0, so that's all good. But this should have been a +3. 12 divided by 3 is 4. 4 and -5 is going to be -1. And -1 is certainly not smaller than -2. So that kind of verifies that none of those numbers to the right should be colored in. My apologies. Hey, we all make mistakes, teachers included. Let's go ahead and take one more example of this. Our goal is to solve for x, so let's get rid of the 12. We're going to get rid of a +12 with a -12, and we're going to be fair to both sides. After all, +12 and -12 make 0, leaving us with x split into -10 parts is greater than or equal to -12. Now, how do we get rid of this division? We're going to multiply both sides by a -10. Oh, and as soon as you hear that, as soon as you hear multiplying by a -10, you know what that means. That inequality sign should flip around. Now, why does this work? Because 10/10 makes a whole, the opposite of a negative. Hey, good. That leaves us with an x. And of course, that x is going to be less than or equal to the opposite of those negatives or positives. 12 sets of 10 or 10 sets of 12 is 120. And just for the heck of it, let's go ahead and go by tens, shall we? Just because we're talking with such large numbers. I'm going to go ahead and draw a closed dot because it can equal 120. And we're going to look for all the numbers that are smaller, which means we're going this way. Make a nice thick ray. And don't forget the arrowhead, because after all, number goes on forever. That means that all those numbers that are now shaded in would make a true statement. Meanwhile, all the numbers that are not shaded in would make a false statement. And by the way, 120 itself would also make a true statement. If you don't believe me, substitute it in. Divide. Add. And while 0 is not greater than, it is equal to 0. This is a true statement. Remember, it's only got to be one or the other. And in this case, it works. Thus, we shaded in 12. Now, speaking of one or the other, let's talk about compound inequalities. Now, you've heard about this term in chemistry or in science class. Compound, composite, basically means it's made up of two or more inequalities anytime you see those letters comp. So, a compound inequality is a sentence with two inequality statements joined either by the words or and. Now, an or statement, you heard what I just said. It can be one or the other. An and statement, however, has to satisfy both. So if I say to be a part of the team, you have to be a part of the school and have a certain grade point average. Well, if you're a part of the school but you don't meet the grade point average, you're not on the team. If you have a great grade point average but you're not part of the school, you're not on the team. So and means it's got to be both, or means one or the other. So I want you to pay attention here. I'm going to graph both of these. Oh, and I'm going to emphasize that word or. It could be one or the other. So if I put a solid circle at 5, because it can be equal to 5, and it can be all the numbers that are greater than 5, all those numbers will work. How about smaller than 2? Of course, that goes on forever. Let's try that again. And can it equal? No, it cannot equal to. We should be using an open circle for the 2. Now I want you to think about that. Pick any number in the left, the middle, and the right section. So let's just pick -5, huh? While this is a false statement, that's true. And remember, for an or statement, it only has to be good for one or the other. So that explains why -5 is colored in. Let's try a number in the middle. Let's try 4. Is 4 less than 2? Nope. Is 4 greater than or equal to 5? Nope. 4 is not good for anything. Thus, don't color that in. Let's try 7. Is 7 less than 2? No. But is 7 greater than or equal to 5? Yes. And since it only has to be one or the other, 7 should be colored in, and 8 and 8, 8.5 and 8.5 trillion. That's what a compound inequality sign looks like. And folks, I don't know if you realize this, but I have been showing you this every day in our title page, kind of giving you a little sneak peek about what compound inequalities are going to look like. Onward, so that's an or problem. Let's see what an and problem looks like. Now this says -4 is less than x and x is less than 7. All right, hold on. Let me write each of these in a different color. So x is greater than -4. Let's pretend the other part of the inequality is not there. Any number works. I'm going to draw this above it, open circle, greater than goes to the right. Okay, let me do the next one in red. So now let's pretend like the -4 is not there. Any number works as long as that number is smaller than 7. So open circle above 7. Notice I'm drawing these above. All right, ladies and gents, what we are looking for is some purple. Where's the red meet the blue to make purple? Okay, so both, okay, there's some area, there's some area, there's some area. All these numbers in between. Now, how about 7 exactly? Well, 7 works for blue, but not for red. So we're going to leave an open circle at 7. How about -4 exactly? Well, -4 works for red, but not blue. So we're going to leave an, but then all these numbers in between, those are all the numbers that satisfy both one and the other. So for instance, if you picked any number like, you know, Mr. Cowan, I'm going to go after 0, right? Is 0 greater than -4? True. Is 0 smaller than 7? True. It's got to be both one and the other. By the way, if this looks kind of almost like it's saying x is in between -4 and 7, I would agree with you. And look at what your graph looks like. All these numbers happen to be in between -4 and 7. Now just let's practice another one of those, shall we? So let's go with the following inequality, compound inequality. -1 is less than or equal to x, and x is less than 5. Let's just do one at a time. So let's pretend like the 5's not there. we can have any number x as long as x is greater than or equal to -1. So right above the -1, I'm going to solid dot because -1's okay, it can't equal it, and there are all the numbers that are greater. All right, let's do the other part now. Let's pretend like the -1's not there. Any number x works as long as x is less than 5. So above the 5, I'm going to draw an open dot. Let me draw that up there. And then where are all the numbers smaller? Okay, there we go. And so now we're trying to find where's the red meet the blue? Where are they both good? Well, if I look right in here, right in there, okay, so that looks good. How about 5 exactly? Now 5 works for the red, but not for the blue, so let's draw a big old empty open dot. How about -1 exactly? -1 works for blue and for red. Well, hot diggity. Therefore, we're going to color that one in. And we're going to color in all these points in the middle. Don't believe me? Check them out. Is 0 greater than or equal to -1? True. Is 0 smaller than 5? True. Okay, let's make it more interesting. How about -1? Is -1 smaller than 5? True. Is -1 greater than -1? No, but is it equal? True. Thus, we colored in -1. However, just to pretend, let's do the 5 again. Is 5 greater than or equal to -1? Yep. But is 5 smaller than 5? Nope. And remember, with the compound inequality that is an intersection, we call that an intersection in high school. It's got to be both one and the other. So notice that I like to draw the little arrows above. Now I can go ahead and erase the work and just show the inequality on the number line. In purple are all the numbers that are both greater than or equal to -1 and smaller than 5. All right, that's going to give you a little taste. I can't even remember if I'm going to put that on the quiz or not. But for now, I want you to focus on solving solving inequalities. You'll see some of those compound inequalities maybe in the challenge problems. That's what I got for you, folks. Take care, do well, and let's grow.